My name is Dean Kuhnke. I'm the Safety Director for Dawson Public Power District, and today we are going to show you our high voltage safety demonstration trailer. It is to try and replicate some of the faults or some of the problems that may go on out in the real world when it comes to power lines and some of the safety aspects that we need to think about when we are around power lines or maybe involved in an accident or something that maybe there's down power lines or down poles, storm situations, things of that nature. So thank you for giving us this opportunity to present to you, and I hope you learned something. So this is our high voltage demonstration trailer. What it is it's a way for us to bring our power lines to you for the sake of demonstrating electrical safety. Right here on this end here, this would be a lot like what you would find at a house service, so to speak. This box here would represent where we would normally have like our meter at, and this voltage down here is 240 volts, and a lot of times going into your houses would also be the 120 volts. The 120 volts is what, powers like our lights and most of our appliances, hair dryers, radios, TVs, things of that nature. For the sake of our demonstration later on, we're going to be using 240 volts. The 240 volts would be like what is used for your air conditioning, or maybe if you have electric stove, your clothes dryer, those all operate off of 240 volts. This is our transformer, and the transformer has no moving parts in it. Its job is to safely change the voltage to our household voltage. The voltage coming into our transformer is 7,200 volts, and out of it, it makes 240 volts. Next, above our transformer, you're going to see what we call our fused cutout. This door here is the fuse, and when closed, will allow the electricity to flow into our transformer. If there is a problem down here somewhere on the transformer side of things, our fuse will blow, and that helps protect the source. The source would be our power line out here. Down low, we have our neutral wire, and up above is our phase wire. Now, at some power companies, they may flip-flop those. The important thing to remember is that this neutral wire is a current carrying conductor, so we have to show it the same respect that we show the phase conductor. We need to realize that current is what is going to harm us or kill us. Voltage is what pushes the current, and the two together form watts. And how we build our electricity is on watt hours, more commonly kilowatt hours. And just like you have breakers in your house that for protection of overcurrent situations, that is what our breaker does. If it sees a fault or an overcurrent situation, it is going to open up. The difference is our breaker will operate several times, giving that fault a chance to clear itself. This would be going back to, so to speak, our substation. Now, what we're doing here for the purposes of our safety demonstration is we're just using another transformer again. And what we're doing is we're backfeeding this transformer with 240 volts. Like I said, there's no moving parts in here, and the transformers, they don't care which way the electricity's flowing. They only have one job, and that is to change the voltage that is incoming to whatever's going out. So here, we are feeding it with 240 volts. It will go through our transformer and out through the high side, and we will have 7,200 volts while we are performing our demonstration. What is so important about this is the fact that if you have a generator at home, you need to make sure that you have a double throw with a center off position switch to make sure that when you are running off of generation power at home, like in the case of a storm, that you are not putting voltage back out on the line for where the linemen are working to restore your power. Electricity is always trying to find a path to ground. It will take any and all paths to ground that it can find. It tends to take the path of least resistance most, but it still will take any and all paths that it can find to ground. How do we control electricity? How do we control where it's going? Well, that's a difference of conductors and insulators. Insulators are how we stop it from trying to find a path to ground. And you'll see an insulator up here at the top end of this pole. You'll also see an insulator up here at the top end of this pole. That's keeping that electricity from going back into these poles, and we're keeping it out on these conductors. Now, I use the word conductor. Most commonly, good conductors would be, metals are very good conductors, whether it be steel, aluminum, copper. That's what we're mainly going to be using for conductors. Later on, we're going to talk about wood and how wood can sometimes be a bit of an insulator, but other times can be a very, very good conductor. I mentioned insulators. What makes good insulators? Rubber can make a good insulator. Porcelain can make a good insulator. Plastics, epoxies, they make very good insulators. You know how when you're at home and sometimes when a lightning storm goes through and your power blinks, your lights go off? Well, that's our breaker operating out there in the field. Our breaker, it tries to give the whatever's causing the fault, whether it be a tree branch or a varmint or something like that, it tries to give it a chance to clear itself. And while it's doing that, it goes off and then on, off and then on, and then it'll go to lockout. And sometimes, depending upon the breaker, maybe they'll operate a third time before they go into lockout. So what we've done here is we went ahead and we put up one of our grounds up here on the line between the neutral and the phase, and that's going to simulate our fault, or maybe it'd be like a tree branch or something. So Joe's going to go ahead and he's going to turn on the power down there. And when he does, if you listen really closely, you're going to get to hear this breaker operate. And then when it goes into lockout, you'll see this yellow tab come down. There's 1, 2, and 3. It goes into lockout. And right there, our yellow tab came down. And that's what the linemen use to know when the breaker is off. Earlier, we were talking about conductors and insulators, and the same thing when it comes to wood. If we're talking about maybe super dry wood, it can kind of be a decent insulator, but not really a great insulator. When we're talking about whether it be green wood or wet wood, they make very, very good conductors. What's important about that? Well, if we get trees into the line, trees can also create that path to ground for electricity to flow. We're going to go ahead and turn on the trailer here, and Tony, he's going to go ahead and demonstrate how that electricity can pass through this green tree branch, because with them tree branches, they also have the sap and the water running through them, which causes them to be a great conductor. Go ahead, Tony. If you look really closely, you can see it just sparkle just a little bit, maybe start to smoke just a little bit. That tells us right there that it's making a path between our phase wire up above and our neutral down below here. And it is most definitely conducting electricity. Also, Tony, he's going to go over here to our transformer, and right across the cutout where the fuse would normally go, that'd be 7,200 volts flowing through there. As you can see, he makes contact with both sides and it lights up our light here down below. That's 7,200 volts going through that tree branch right now. Do we have any kids out climbing trees? Let's make sure that those trees that they're climbing aren't near any power lines, because if they get to bouncing around up in there and then branches come into contact with the power line, right there, we could have another case of that electricity finding a path to ground. Trees that growing up into the power lines, that creates line losses, because when those trees grow up into the power lines, that electricity is finding another path to ground. That is costly to both the company and the customers. Therefore, it is very important that if you have any trees on your property that are growing up into the power lines, please contact your power company so that they can get out there and get them trimmed, and it saves everybody money and also could save lives or any harm that could happen to someone. As you can see here, we've taken kite string and we put it over our fuse here. We do not actually have a fuse in the fuse tube here. We're just using this kite string. Why is that important? Because if you're out flying kites, you want to make sure that you stay away from power lines because they too could also be a conductor. Make sure you look up, look around before you fly any of your kites. Make sure that you're a safe distance away from any power lines. Also, if your kite would happen to ever come in contact with a power line, do not try to remove it yourself. Make sure that you call your power provider and we will come take it down for you. That includes mylar balloons, foil balloons, or your kites or anything of that nature. If it gets into the power line, call your power company. We will come take it down for you safely. He's going to go ahead and close in this fuse door here that we got the kite string on. And bam, it lights up the light. There's 7,200 volts going through our kite string right there. And now we've gone ahead and we've attached a kite string into a hot tap and put it up on our phase wire. And then we went ahead and we tied a washer to the end of it. So when Tony lets go of that string, it's going to swing down in, the washer is going to swing down into that neutral wire, and you're going to get to see it arc between the phase and the neutral, conducting that electricity through that kite string. And so you notice that we're wearing a lot of safety apparel here also. We're wearing hard hats, safety glasses. We all have on FR clothing. You also notice that Tony and Joe, they're wearing rubber gloves. Now these rubber gloves, this is a specific type of rubber. It is very clean and very pure and is there for their protection. Some people might think, oh, well, you know, I've got rubber-soled shoes on, so I should be insulated. Well, we've got a rubber-soled boot here to prove to you that there are impurities in that rubber. It is not necessarily a great insulator for protection. There are boots and shoes manufactured specifically for that, but not all. So this here boot, Tony's going to show when it gets over in contact with the line that it is still a very good conductor. Another thing we want to think about is whenever we get around power lines, whether it be like, say, lifting up irrigation pipe or something along those lines, where do we usually store the irrigation pipe at? Is it near the end of the field? What else is at near the end of the field? That's where our power lines are at also. So it's extremely important whenever we're handling long objects that we look up, look around, make sure that the scene is safe for handling those objects. And so now you'll see that we have a tire in our little test box here. What are we talking about tires for? Well, maybe we're talking about auto accidents, and if we get into contact with a down power line, maybe hit a pole or something like that. Well, earlier we talked about rubber as a good insulator. We talked about that rubber in our rubber gloves, like what Tony and Joe are wearing, is a good insulator. But we also talked about that the rubber in our boots wasn't necessarily a great insulator, or in our shoes. Why is this rubber not very good insulator? Well, in our car tires, there's the impurities, there's carbon, things like that inside the rubber on the car tires. Also, we've got steel belts in the car tires. Those steel belts, steel being a metal, makes a very, very good conductor. So we're going to go ahead right now, and Tony's going to demonstrate here on how good of a conductor this tire actually is. So as you can see, it can make a very good conductor. Why is that important? Well, if we're ever involved in an accident with down power lines and we're in that vehicle, we need to stay in that vehicle so that we don't create a path to ground. By staying in that vehicle, we're just like that bird up here on the wire. We are not creating another path to ground. We are just at that one potential. So if we stay in the vehicle, we're going to be safe. The only time that we would ever want to get out of the vehicle is if the vehicle was on fire. And then at that point, it is very important that you follow these next few steps. You want to open the door and then position yourself so that you can make a clean exit. Keep your arms together, and then you're going to get up and you're going to jump Keep your feet together. And then you're gonna hop away or shuffle, real short shuffles until you get at least 50 feet away. A lot of the things that we've talked about relate to touch potential. However, when we get to talking about car accidents or down power lines and we're in the vicinity of a down power line, we also need to be thinking about step potential. Step potential is a lot like throwing a rock into a pond or into a lake and you get that ripple effect where you see them waves go away from where you threw in the rock. Well, that's the same way when we have a down power line. A lot of times right where that down power line is at, we'll have that system voltage. But these rings represent, as we get steps away or several feet away, how that electricity may dissipate through the soil. And it all depends on the soil conditions of whether or not there's a lot of sand or is a lot of clay, is there a lot of moisture? What makes up that soil depicts on how big this area is. So we always recommend when it comes to down power lines that you stay at least 50 feet away. If somebody is in that vehicle and there's no harm, make sure that you do not get any closer than 50 feet to that vehicle and make sure you tell them to stay in that vehicle because right then they're just like that bird on the wire. They're only at that one potential. So we take our personal protective equipment very seriously. One of the things that I mentioned earlier is our rubber gloves. It is very important that we take care of them. And that's the reason why they got these heavy duty leather protectors on the outside of them, because even one little pinhole in these rubber gloves, and that's all it takes for that electricity to find its path to us to possibly find that another path to ground. So what we've done is we've got this reject glove that we on purposely put a pinhole in the end of it. Plus we also stuck a hot dog in that finger to mimic your own finger. Why do we use a hot dog? Because it's made up of meat, fat, water, just like all of our bodies are. So now Tony's going to demonstrate how that electricity is going to find that little pinhole when he takes and puts this metal rod up against the neutral and then brings it up into the phase wire. So we went ahead and we took the hot dog out of our reject glove that had the pinhole in the end of it. And you can see right here on the very end of the hot dog, it just made the littlest entrance. But that little entrance also on the inside did a whole lot of cooking on the inside of that hot dog. And that's what that high voltage does to us. Why is that important? Because when it comes to a high voltage burn, even as much as what we enjoy and appreciate our local hospitals, we need to get these people to a burn center right away so that they can get the treatment that they need to maybe possibly save appendages, because we need to get them to those experts that understand with these electrical burns that they are burning from the inside out, just like your microwave oven. So here's an example of a rejected glove. And the reason why this one was rejected was because of this tiny little hole over here. Some of the other thing, and you'll notice that you can see that yellow that's on the inside of the gloves. That's the reason why the gloves are yellow on the inside, is so when doing the visual inspection on the outside, if you see a hint of that yellow, you know that you have a hole or a weak spot. Another thing that we're going to do is we're just going to look all around the glove, check to see if there's any cracking or anything like that of the rubber. We'll be looking in between all of the fingers and the thumb. We're going to be checking to see if we see any bad spots, giving it a really good visual inspection. Along with doing the visual inspection before we use our rubber gloves, we're also going to do an air test. We're going to roll up our glove, trapping that air in there, making it to where we end up forcing them fingertips to blow out, like so. Along with the visual inspection and the air test inspection, monthly our gloves are sent into a testing laboratory where they are tested at 20,000 volts to ensure that they are dielectrically safe for us to be using. There are different classes of gloves, But our gloves that we use typically on a day-to-day basis are the class 2 and tested at 20,000 volts. Using a hot dog, because of the fact that it best represents our human body of what's going to happen when we get it into high voltage. We got our hot dog up here on the end. Tony's going to go ahead and he's going to take our metal rod, put it up against the neutral, and then ease that hot dog up into the line so you can see what happens when you get into a high voltage contact. When you look at this hot dog, you can just barely see right here on the end where it made the entrance of the electricity. But if we open up the hot dog, we're going to see where it did a lot of, so to speak, cooking on the inside. So these high voltage burns, they can actually, for the lack of a better term, cook you for up to 3 days on the inside. So that's the reason why it's so important that we get to a burn center so that we can get that much needed treatment from the experts that understand them. One of the things that we need to think about also is maybe we're doing some home improvement projects around the house, or maybe it's even for work that we're possibly having to climb ladders or something like that. We want to be really aware of where power lines are at, that we don't get them ladders into a power line. Also, whether it be, any type of farming equipment, we want to be really careful of where those augers are at, whether it be on the combine or the grain cart. Maybe you own your own sprayer, or you work for a fertilizer company and run a sprayer with them big overhead booms. We need to be very careful when turning at the ends of the field. Also going out for all those people that maybe work for irrigation well companies, getting those booms up in the air when working on wells of any type, whether it be our residential wells or our irrigation wells, any type of boom operator, maybe a concrete pumper or any of those things, cranes doing construction work. We need to really stop, look around, assess the scene, make sure our work area is safe to proceed, look out for those power lines or any other obstructions. Next, we're going to go ahead and we're going to show using our household voltage of what happens when humans come into contact using our hot dog, if they come into contact with electrical wires. Right here, this is going to be 240 volts. This will be just like what is used in your air conditioner, your clothes dryer, if you have an electric stove. That's the voltage that we're talking about here. So without further ado, we're going to go ahead and we're going to show how that all works. You can see he's coming into contact there, and it's a violent burn. You can probably even hear it just a little bit sizzling and the smoking on the outside. And you notice that you're really not seeing much damage there on the outside, just kind of like when that high voltage, but I guarantee you it's doing a lot of damage on the inside. Next, we're going to go ahead and we're going to use a pickle. Why are we using a pickle? You're going to see just in a moment. We really want to show that how great a circuitry our bodies make, because with our blood vessels and our nervous system and everything, we've got great circuitry on the insides of our bodies. So right here, when we turn this on, this is going to just kind of give you X-ray vision of what's going on inside our bodies when electricity's passing through. Once again, this is 240 volts here. You can see it's just lighting it up on the inside, and that's what's going on with your bodies. There's not really any damage going on the outside, but it is doing all sorts of damage on the inside of your body. Thank you for taking a moment with us today. I'll just leave you with these words. The thing that we need to remember is electricity, it demands our respect. It requires our respect. Electricity does not discriminate. It does not care whether we're male or female, whether we're rich or poor, whether we're old or young. If we do not show electricity the respect that it deserves and demands, electricity will shock us and could possibly even kill us. So please, please, whenever you're using electricity or around power lines, make sure that you're thinking safety first. Thank you.